the development of the area formulas, this is the one I love the most. So in G-GMD.A.1, activity number 4, we investigate finding the formula for the area of a trapezoid. And that formula is not a trivial one. Of all of the formulas, my belief is this one is the one we don't know where it comes from. We get the rectangle, we get the parallelogram, we get the triangle, we get those. They're visually connected. This, when I look at base 1, base 2, height, and so on, they're not quite as connected. Now, just maybe quickly to talk about that, in a trapezoid there are always 2 parallel sides, and so I'm going to assume you know that, and these are, you know, the base 1 and the base 2. The height is within the shape, and so on. So maybe I should have put base 1, base 2 on all these. And there isn't, there's not like base 1 is always the bottom or anything like that. It's just a name for 2 bases, okay? I want to show you 1, 2, 3 different ways to do this briefly, and maybe we'll look at a couple of them up close for you. But the first one is called doubling, and this is a neat one, really neat one. So if we take this shape and we flip it on its back, like a turtle landing on its shell, it would flip upside down and look a little bit like this, I believe. So do you understand what I did is I took this guy, popped it on its back, and this here would be B1 and B2. And guess what shape it creates? In this case, a parallelogram. And we know a parallelogram is base times height. Now, take a look at our base. Our base is B1 plus B2. Our height is h. So there's the formula for that parallelogram. But we don't want the area of a parallelogram. We want the area of 1/2 of that, because we doubled the trapezoid. If you want the area of one trapezoid, you would divide that entire region in half. Same thing if it looked like this. We would place it on its back. It would land in there. This time maybe it's a rectangle instead of a parallelogram. Same idea. It would be B1 plus B2 would be the base. The height would be here. And again, we only need half of it. Doubling. Very cool little technique. In a similar way, cutting things in half, does the same process. So instead of doubling, we're going to pull out our scissors and we're going to cut this guy in half. And we're going to lay the half down here. So again, it would lay into something like this. This is our B1 and our B2. Once again, a parallelogram is formed, and its dimensions are exactly B1 and B2, and this dimension is half of the height. There it is. One more time over here. If I lay this one, or cut it in half, this would lay into this position, and we would have a base of B1 plus B2. Our height will be exactly 1/2 of the old height, and so that rectangle would be 1/2 of the height times B1 plus B2. Beautiful stuff. Great way to make sense of a formula. The last one is quite a bit fun too, and it has a lot of good review algebra hiding in it in terms of establishing these things. But the idea is that trapezoids are made up of smaller shapes. You might see it as 2 triangles, and if you add those 2 areas together, you get this formula. You might see it as a rectangle and as a triangle, and if you set up those, they would simplify out to giving you this formula. You might see it as, let's see, I don't know, a parallelogram maybe, and a triangle, and that would also do it. It's beautiful math, simplifies out. We'll show you a little bit of that, but very cool stuff. So let's look at this trapezoid a little closer. Let's try a technique called the doubling technique. So the idea is to obtain the formula of a trapezoid. We want to double this area, this region. So what we're going to do is we're going to rotate this about this guy here, about this midpoint of this leg, and drop it over here.
and it would look something like this. Now what's cool, if you look at the full green region now, this is a parallelogram. And we know parallelograms are base times height. The new base is B1 plus B2, this whole region, times the height would give us the entire region. But we only want half of that. So what we would do is we would take one half of the value of the height times B1 plus B2, and we would obtain that region. It would even work again if this guy was more rectangular in shape. You can see that. There's your height times B1 plus B2. And again, divided in 2 because you only want half of that. A very cool little relationship there. The halving technique works as follows. We would take some sort of line that would cut the height in a perpendicular manner, cut it exactly in half, a perpendicular bisector there, cuts it exactly in half. Now, that would allow this top piece to be rotated into this spot. And potentially, so it's gone from there and it's here. Now we've got the same physical region by dissection, but it's all down in this area. And the new dimensions of this parallelogram are B1 plus B2, that's good, times half the height. That's exactly our formula one more time. So cool that this formula keeps appearing in some nice little ways. And again, that wouldn't matter if we were in this format or this format, it would still continue to work just fine. The idea of composite area is to take a shape and cut it into smaller shapes that you'd recognize. So let's pretend, this is a trapezoid that looks like this. I might drop this down and form this rectangle and this triangle. And all they have you do is kind of calculate those two regions and add them together. So in the case of the rectangle, it would be the B1 times the height. That would be the rectangle. And in the case of the triangle, it would be 1/2. Now, what is our base here? Oh, a little bit of thinking here. This little region would be B2 minus a B1, because the entire length is B2, and so we would have to subtract this region to get this region, which is B2 minus B1. So it would be B2 minus B1, and then again times the height would be the triangles region. Now this looks nothing like our trapezoid formula, but with a little bit of work you'll see it will turn out to be. Here's B1H plus 1/2 B2H minus 1/2 B1H. This is just simply the distribution of this right here, if you multiply that out. And what we notice is, and it looks a little tricky for students to notice, but they notice B1H and B1H. And you have 1 B1H minus 1/2 of B1H is 1/2 left over of B1H. And then what still remains is the 1/2 B2H that's sitting right here. So when we combine the like terms, guess what happens? I see that there's an H and a 1/2 in both of these, and when I factor it out I get B1 and B2. This is a very recognizable formula that we wanted to see. Composite area would come in all different types of forms. Let me just give you a few examples. Algebra for all of this, but I am going to at least show you some different ideas. You could split something into a triangle and another triangle. You could split it into a parallelogram and a triangle. You could split it into two triangles and a rectangle. You could split it into, I guess the point I'm making is you could do all kinds of things. You could, split it up into lots of little pieces and calculate those pieces. And so the idea is, if you do this correctly, no matter what shape is formed, or many shapes are formed, they, when you combine them, will obtain the same formula. And so that awesome little formula of 1/2 base 1 plus base 2 times height is taking care of all of the different parts and pieces possible. And so it's a super cool formula.